Dear students, having discussed various aspects of how coupling happens between two nuclear spins, we are going to see some other terms that are related to coupling phenomena, such as quadrupole broadening and spin decoupling. Okay, so usually protons with a nuclear spin quantum number is equal to 1 by 2, such as proton or carbon 13, have got a spherical nuclear charge distribution, whereas nucleus such as nitrogen, uh, bromine, chlorine, etc., they have got a nuclear spin quantum number greater than 1 by 2. For example, for nitrogen, I is equal to 1. And such nuclei, instead of having a spherical nuclear charge distribution, they rather have an ellipsoidal nuclear charge distribution. And because of this virtue of this property, the nuclei of these atoms normally possess a nuclear quadrupole moment. Okay, so what happens is in NMR experiment, uh, this the nuclear magnetic moment of the nucleus can couple with this nuclear quadrupole moment. Okay, and this affects the rate of nuclear transitions between the lower energy nuclear level and the upper energy nuclear level. Say for example, as you know that proton nucleus has got a two nuclear spin states only, whereas nitrogen, which has got a I is equal to 1, has got 3 nuclear spin states, where the lower energy spin state has got Mi is equal to 1. Then the next nuclear spin state has got Ma is equal to 0, and the highest energy nuclear spin state has got Ma is equal to -1. So there are 3 nuclear spin states with Ma is equal to 1, 0, and -1 in the order of increasing energy. Okay, so nuclear transition can happen uh, between these nuclear energy levels. For example, from Ma is equal to 1 to Ma is equal to 0, or Ma is equal to -1. And because of coupling of the nuclear magnetic moment with the nuclear quadrupole moment, in case of nuclei with I is equal to I greater than 1 by 2, the nuclear transitions between the lower energy nuclear level and the upper energy nuclear level speeded up. Okay, the transition rate increases to a greater value, and because of this very rapid transition rate, the nuclear will tend to reach a Boltzmann equilibrium, where the population in the upper nuclear energy state becomes is equal to the population in the lower energy state. Okay, so we call this as a saturation situation, so that the upper energy state cannot take any more population from the lower energy state. Okay, so this saturation condition actually causes the adjacent proton nuclei to get confused, because the adjacent proton nucleus, when it tries to couple with the nitrogen nucleus, for example, okay, the adjacent proton nucleus cannot actually decide whether the nitrogen nucleus exists in the lower nuclear energy state or upper nuclear energy state. Okay, so when the adjacent proton nucleus tries to couple with the lower energy nuclear state of the nitrogen nucleus, the population gets immediately transferred to the upper energy state of the nitrogen nucleus. Okay, and then if the proton tries to couple with the upper energy nuclear state of the nitrogen nucleus, the population rapidly reverts back to the lower energy nuclear state of the nitrogen nucleus. Okay, so this shuttling of the population between the very fast shuttling of the population between nitrogen between the nuclear energy levels of nitrogen nucleus actually leads or actually prohibits the adjacent proton nucleus to couple with it. Okay, so the adjacent proton nucleus will become effectively decoupled from the nuclear spin states of the nitrogen nucleus. So this process of decoupling of the nuclear spin state of a proton nucleus by an adjacent nucleus which has got a high quadrupole moment is called quadrupole decoupling. Okay, I know that you didn't get the concept quite to the to the same percentage, but once we consider 3 examples or 3 typical cases, you will be able to understand it better. Okay, for this for this in order to understand this process, we are going to consider three cases where we are going to consider a quadrupole nuclei with a small quadrupole moment, okay, then a quadrupole nuclei with a large quadrupole moment. We are considering the two extremes, and we are going to consider somewhere in between, whereas we are going to consider a nucleus with a moderate quadrupole moment. So first of all, let's take the nucleus with a small quadrupole moment. Examples are nitrogen nucleus in a symmetrical environment, okay, in a symmetrical electronic environment, such as the nitrogen in NH4 plus, where the nitrogen is being surrounded by 4 hydrogens to symmetrically around the hydrogen to the same extent, or the nitrogen is in CS3 in S3 plus, okay, or a quaternary nitrogen such as R4 N plus. In all these cases, the nitrogen nucleus is being surrounded by electron distribution, bonding electron density to some symmetrical extent, okay. And here is an example, typical example of a proton NMR spectrum of CS3 NS3, where we have got the nitrogen nucleus in a symmetrical, and we have one here which is being taken in water with a pH less than 1 condition. And as you can see from the NMR spectrum, you can see that the NMR peak of CS3 proton, okay, of this unit of the molecule here, CS3 proton gets split into a quadruplet. Okay, so this obviously happens because the three CS3 protons here couples with the 3 protons of NS3. Okay, so according to the n+1 rule, the 3 protons splits the peak of NMR peak of the CS3 protons into 3 plus 1 for a quadruplet. Okay, and if you see the NMR peak of the hydrogen which is being connected to or the protons which are being connected to nitrogen here, these protons can couple with the 3 protons of CS3 group, okay, so and as well as it can couple with the nitrogen which has got a quadrupole moment, okay. So since this proton here couples with its neighboring nitrogen which has got a nuclear spin state of -1, 0 and +1 in the order of decreasing free energy, then because of coupling with this nitrogen nucleus, okay, the peak will be the NMR peak of this proton will be split into a triplet, okay. So because it has to follow the 2 Na+1 rule, okay, and I is equal to 1 here and N is equal to 1, so 2 Na+1 is 2 plus 1 is equal to 3. So the peak of the proton will get split into a triplet pattern with a 1:1:1 ratio. That's exactly what we see here. We get 3 peaks here with the equal intensity because the proton couples with the 3 protons in here couples with the nitrogen, okay. Again, the 3 protons can couple with the 3 CS3 protons, and according to the n+1 rule, each of the peak gets split into 3 plus 1, that means a quadruplet pattern, okay. So you can see it here. This is the splitting pattern. We have got the NMR peak of the 3 protons here, and since the 3 protons couples with the nitrogen which has got 3 nuclear spin states, each of the peaks gets split into a triplet pattern with a 1:1:1 intensity ratio. And since the 3 CS3 protons couples with the 3 methyl protons, each of these lines gets split into quadruplet pattern with the quadruplet intensity ratio. So you can see 3 peaks in the triplet, and each peak again gets split into quadruplet pattern with the intensity ratio 1:3:3:1. Okay. So this is what happens when the protons couple with a nucleus with a small quadrupole moment, okay. So for nuclei with a small quadrupole moment, the proton will be able to distinguish each of the nuclear spin states of the nitrogen or nitrogen nucleus here, okay, and the proton will be able to couple with each of the nuclear spin states of the nitrogen atom here, okay. But what happens when the nucleus has got a very high value of quadrupole moment, okay? Examples are nitrogen in asymmetrical electronic environments, then chlorine, bromine, iodine, etc. They have got a very large value of quadrupole moment, and this quadrupole moment can couple with the nuclear spin states of the atom. Okay, and as a result, what happens is the nuclear transitions approach very rapid rate because of the coupling between the quadrupole moment and the nuclear magnetic moment. And what happens is when the adjacent proton tries to couple with the nuclear spin states of say for example nitrogen in a symmetrical environment, the proton will see a time average view of the nuclear spin moment, okay, rather than individual nuclear spin moments, okay. And the proton will experience a net effective nuclear magnetic moment of I effective is equal to 0, okay. And the proton will be able to couple with only the time average view, but not with the individual nuclear spin magnetic moment of the adjacent nitrogen atom. So if the effective coupling doesn't occur between the proton and the individual nuclear spin states of the nitrogen atom. So instead of seeing a multiplet pattern like we have seen in the earlier spectrum, we see only a single pattern for the proton. So that means the proton is effectively decoupled from the nitrogen nucleus, and this effect is frequently observed in aromatic amines such as substituted anilines. The third case is a nucleus with a moderate quadrupole moment. So we have seen two cases where the nucleus has got a small magnetic moment where the adjacent proton can distinguish each of the nuclear spin states of the quadrupole moment nucleus and couple with them. Then we have seen the case of a nucleus with a very high value of quadrupole moment where the adjacent proton cannot distinguish individual nuclear spin states of the quadrupole moment nucleus. But the third case is an intermediate case where the nucleus has got a moderate quadrupole moment. Here the attached proton is not actually sure what it sees, okay. It gets confused and it doesn't actually cannot distinguish whether the individual nuclear spin states of the quadrupole moment nucleus or whether it is the time average view of the nuclear spin states of the nucleus, okay. So rather it gets confused, and as a result neither we see a peak splitting due to coupling with the quadrupole moment nucleus, nor we see a singlet pattern due to decoupling with the quadrupole moment nucleus, but rather we see an intermediate effect where the NMR spectra of the proton gets broadened, okay. So peak broadening happens because of this coupling with the nuclei with a moderate quadrupole moment, and this effect is called quadrupole broadening. Okay, we are going to see another intriguing aspect of or a strange aspect of a coupling phenomenon, which is called deceptive simplicity. In order to understand the concept of deceptive simplicity, let's consider a nuclear spin state or nuclear spin system such as A prime X system, where the nuclei A and A prime are two magnetically non-equivalent nuclei, because in the sense that A and A prime coupled with any other nuclear spin states in the system to different extents. That means say for example the coupling constant between A and X would be different from the coupling constant between A prime and X, but both the nuclei A and A prime are chemically equivalent nuclei. That means the resonance frequency of the nuclei A and A prime would be equivalent, okay. So there A and A prime are chemically equivalent nuclei. They show up in the mass spectra at the same frequency, but they are magnetically non-equivalent because A and A prime coupled with the X nuclei to different strengths. So we can have two different coupling constants, one representing the coupling between the A nucleus and X nucleus, and another coupling constant that represents the coupling between A prime nucleus and X nucleus, okay. And because of coupling between X nucleus and A nucleus, we would expect that the signal of X is split into a doublet, okay. So we get a doublet pattern because of coupling between X nucleus and A nucleus. And since X also couples with A prime nucleus, each peak in the doublet should be split into another doublet. Okay, so we expect a doublet of doublet due to coupling of X with both A and A prime. But simulations shows that it could also happen that the signal of X can be seen as a triplet. Okay, so if the signal of X has to be seen as a triplet, then the coupling between X and the nuclei A and A prime should be equivalent or similar. That means JAX should be equal to JA prime X. So that implies that the nuclei A and A prime, they should be acting like they are magnetically equivalent. Okay, so instead of behaving as A and A prime, both the nuclei should behave as an A2 nucleus, such as instead of representing as A prime X, it should be represented as A2X. So the system behaves like an A2X system rather than an A prime system. Okay, so we see a triplet pattern rather than a doublet of doublet spectral pattern. So we would rather mistake this one, the system, as an A2X system very easily rather than as an A prime X system. So we get deceived by the simple appearance of the NMR spectral peaks, and this phenomenon is called deceptive simplicity, and the spectrum that we get is deceptively simple spectrum. Another phenomenon that we are going to account for is virtual coupling. Here we consider a spin system such as ABX system, where A and B are two chemically equivalent nuclei. That means they resonate at the same frequency on the delta scale or chemical shift scale, but they are slightly magnetically non-equivalent. Okay, both A and B are slightly magnetically non-equivalent. That means A and B couples to the nucleus X to slightly different extents. Okay, JAX and JBX should be slightly different. Let's assume that JAX is 0. That means the coupling between A nucleus and X nucleus is 0. There is no coupling between A nucleus and X nucleus. And the coupling constant between B nucleus and X nucleus, JBX, is non-zero. That means there is some effective coupling between the nuclei B and X. Okay, so since X couples with only B nucleus, we expect that the signal of X is split into doublet due to coupling with the B nucleus. Okay, so that's what usually we expect. But simulations again shows that the signal of X rather could appear as a doublet of doublet rather than as a single doublet. Okay, as if X couples not only with the B nucleus but also with A nucleus. Okay, and here we get a larger coupling constant. Instead of JBX, we see a slightly larger coupling constant, J prime BX, but which has got a magnitude slightly less than JBX. And again we would see another smaller coupling constant, J prime AX, so that JBX is equal to J prime BX plus J prime AX. This J prime BX, okay, that we see here actually arises due to a second order or virtual coupling between the nucleus A and X. Okay, which usually happens between strong coupling between A and very strong coupling between A and B nucleus, because they are chemically equivalent and more or less magnetically only slightly magnetically non-equivalent. Okay, and again this does not happen due to any direct coupling between A and X. This is a virtual coupling which happens through the nucleus B. Here is an example. We have got A nucleus, B nucleus and X nucleus here, and we since we assume that there is no coupling between A nucleus and X nucleus, since there is no coupling between A nucleus and X nucleus, only B and X couples with each other. So we would expect a doublet pattern for B nucleus, but X nucleus, but rather we see doublet of doublet pattern as if X couples with both B nucleus and A nucleus. So here both A and B are very strongly coupled nuclei. That means they are chemically equal and resonant at the same frequency. So coupling happens by virtue of having B nucleus as an intermediate nucleus between A nucleus and X nucleus. Here is an example. Here we assume that the coupling constant between A and B nucleus is 10 Hertz and coupling constant between B and X nucleus is 7 Hertz. They are only slightly magnetically non-equivalent. And we assume that JAX is 0 because A and X nucleus does not couple. Okay. And if the spectrum is being measured at a condition that delta nu AB, that means the resonance frequency between A and B nucleus is 40 Hertz. That means the A and B nucleus are not that much chemically equivalent. Okay, then for X nucleus we would be seeing a doublet pattern. Okay, because X can couple with the only B nucleus. Okay, and but once the separation between the resonance frequencies of A nucleus and B nucleus gets reduced, that means when A and B nucleus becomes more isochronous or having more similar chemical shifts, then the separation between the doublet of X nucleus gets reduced. Okay, and once the separation between the resonance frequencies of A and B nucleus gets further reduced, when it becomes 10 Hertz, the separation between the resonance frequencies of X nuclei becomes further reduced and each peak gets split into doublet. Okay, so right now we can see the effect of coupling between A and X nucleus. Okay, the coupling between A and X nucleus happens virtually through the B nucleus. So once the separation between the resonance frequencies of A nucleus and B nucleus gets reduced to 5 Hertz, you can see that this splitting becomes more prominent. Okay, as if we get a doublet pattern, as if X nucleus couples not only with B nucleus but also with A nucleus. Once the coupling constant becomes or the frequency difference between the A nucleus and B nucleus becomes 1 Hertz, that means they becomes really isochronous with each other, then you can see that the central frequencies the central frequencies that we hear, these two frequencies or these two lines, they come close with each other, they merge with each other and forms this pattern here with the peripheral peaks on or terminal peaks on either sides. Okay, so they rather try to mimic a triplet pattern here. And once you see that the chemical shift difference between A and B nucleus is 0 Hertz, that means when A and B nucleus becomes absolutely isochronous with the the maximum possible chemical equivalence, then we can see that the central peaks are completely merging with each other, forming a rather single peak with a slightly higher intensity, and resulting in an overall peak pattern that resembles a triplet spectrum or triplet pattern. And you can see that here the system behaves as if the X nucleus couples with both B nucleus and A nucleus. Okay, but in reality the coupling between A and X nucleus is 0. So here coupling happens virtually through the B nucleus. X nucleus couples with the A nucleus through the B nucleus. So this is called virtual coupling. Here is an example. We have got the proton A and B nucleus, and when the NMR spectrum of this molecule is being measured in CdCl3 solvent, you can see that the peak of A and B nucleus can be seen separately with a large chemical shift difference. So both A and B nucleus are not magnetically equivalent here. Okay, and the NMR spectrum or the peak of the C nucleus can be seen as a doublet of doublet pattern. Okay, just as if the C nucleus couples with both A and B nucleus. Okay, and once the NMR spectra of the same compound is measured in deuterated acetone solvent, you can see that the NMR peak of both A and B nucleus, they come close together, coalesce with each other or merge with each other, forming a single peak pattern. Okay, that means A and B nucleus, they become more isochronous. As a result, these two, the NMR peak of the proton nucleus, they come close together and the central peaks merge with each other, forming a triple type pattern. Okay, and here the C nucleus couples with the C nucleus couples with the B nucleus, but the coupling constant between A and C nucleus is negligible. So, but rather we see as if there is coupling between A nucleus and C nucleus. So, this virtual coupling happens between C nucleus and A nucleus through the intermediate B nucleus. And next here we have a pictorial diagram, energy level diagram, that shows how the coupling happens. Okay, suppose consider two nuclear spin systems, A and X spin systems. Okay, and consider that we are going to consider the initial case where we consider different possible configurations of nuclear spin states of A and X nucleus. The lower energy configuration is that we have both the nuclear spin states of A and X nucleus. The spin state of A is represented in green color, the spin state of X is represented in blue color. So when both the nuclear spin states of both the nuclei aligns with the direction of the external magnetic field, the nuclear spin configuration will have the lower energy. That's what we show here. Okay, but whereas when we have the nuclear spin states of both the nuclei align in opposite direction with respect to that of the applied magnetic field's direction, we have the most highest energy situation here, which is being shown here. And the next two other possible configurations are shown here with the nuclear spin of X nuclei down, and A nucleus has got an up spin, and then the next possible configuration is that A nucleus has got a down spin and X nucleus has got an up spin. So both these nuclear spin configurations are equally probable, and they should have the same energy. They should be degenerate, but for the sake of clarification, or for argument's sake, we slightly shift the energy scale here in order to see how the transitions happen in our energy level diagram. So initially we assume that the coupling between A nucleus and X nucleus is 0. That means there is no effective coupling between A nucleus and X nucleus, and we are going to see how the nuclear transition could happen for this nuclei. Okay, so in order for nuclear transition to happen, the nuclear spin state of the corresponding nucleus should reverse its spin. Okay, so let's start from the lower energy level and look for X transition, or the nuclear transition of X nucleus. And if you see, we have got a downspin for X nucleus here, and the upper energy state that has got an upspin is this state and this state. Okay, so transition could happen from here to here, and from here to here as well. But since this is energetically more favorable, transition could happen from here to here. So this one is one X transition, and the other transition that could happen is between this state. This one here, we have got a downspin for X nucleus and upspin for X nucleus here. So the transition could happen from here to here. And if you see the energy difference between these two, or energy difference required for these two transitions, or the energy required for these two transitions, you can see that the energy is the same. That means both these transitions would appear at the same energy scale or at the same frequency scale. That means, in other words, in the NMR spectrum on chemical shift scale, both the X transitions would appear at the same frequency. You will see a single peak for the X transition, X nucleus, in the NMR spectrum if the coupling between the A nucleus is 0, or coupling with the A nucleus is 0. Similarly, if you look at the A transition in the absence of coupling with the X nucleus, you can see that the A nucleus has got a downspin here, and the next possible transition could be to this energy state, because the nucleus has got an upspin here, so down to up. So one transition could happen between these two energy levels. Then the next probable transition is between this energy level where the A nucleus has got a downspin, and this energy level where the A nucleus has got an upspin, so down to up transition. So this one is another A transition. And so if you count or estimate the energy required for both the A transitions, you can see that the energies are equivalent. Okay, so this means that in the NMR spectrum, both the A transitions would appear at the same frequency in the chemical shift scale. You will see just one peak for the A nucleus in the NMR spectrum. Okay, so this happens in the absence of zero coupling between both A nucleus and X nucleus. But what happens when we have coupling between A nucleus and X nucleus? So when coupling happens, since these two configurations, since they align with each other, when both the nuclei interacts with each other or couples with each other, the energy of these two energy levels will be raised to some extent. Okay, whereas these two nuclear energy or nuclear spin configurations, where the nuclear spin states are anti-parallel to each other, these two energies, or the energies of these two configurations, will be lowered to some extent. Okay, so here the energy is raised by a factor of plus C, and again here plus C here. Here the energy of the nuclear spin states are lowered by a factor of minus C and minus C here, and the energies of all these plus C and minus C should be exactly equal. They should have the same magnitude. And right now we have got a new nuclear energy levels in presence of coupling between A nucleus and X nucleus. And let's look at the X transitions. As said previously, X transition could originate from this energy level and end up in this energy level, and you can have also one more X transition that originates in this energy level and ends up in this energy level. So right now, if you count this transition as X prime transition and this one as X double prime transition, you can see that the energy required for X prime transition is lesser compared to the energy required for X double prime transitions. Okay, so this represents that, or this shows that the NMR peaks corresponding to both these X prime and X double prime transitions would be appearing at two different frequencies in the chemical shift scale. You will see two peaks for X transitions because X couples with the A nucleus. Okay, so the NMR spectrum, NMR peak of X nucleus gets split into a doublet due to coupling with the A nucleus. Similarly, if you look at the A transition, you have a lower energy transition here and a higher energy transition here, which are respectively called A prime transition and A double prime transition. So because A couples with X, we see this effect. So because of coupling with X nucleus, the peak of A nucleus will be split into two. Okay, a doublet pattern with one of the doublet, one peak of the doublet at a lower energy and another peak of the doublet at a higher energy. So this is how coupling between two nuclei splits its individual nuclear spin peaks into a doublet or triplet or quadruplet, or and so on.